Alright folks, in this radiation video we're going to discuss the types of nuclear decay and the differences between them. So for this we have three major types. So alpha particles, let's discuss those and talk about where they come from. So let's say we have a material like uranium. I've got uranium-238. It has protons, it has neutrons. I'll tell you, it's got 92 protons and 146 neutrons. What happens to uranium when it goes through a decay is it will give off an alpha particle. Part of the nucleus breaks out. It just tries to collapse, shoots a little bit out as the rest collapses into a tighter shape. And so what gets out actually has protons and neutrons. It has two of each. Well, then there's something left over that will have protons and neutrons, and it will have whatever's left. So it'll be 90 protons and 144 neutrons. Which means whatever this is has 234 pieces, 90 of which are protons. Well, that's not uranium. Remember, protons define the element. So it is now thorium. What actually happens is uranium turns into another new atom because, remember, all that defines atom is the number of protons. It shed 2 protons and 2 neutrons and became thorium. Well, 2 protons and 2 neutrons is a helium-4. So an alpha particle is a helium-4, and because it comes from a nucleus, it doesn't have its own electrons at that point. It's just the nucleus. It is just the nucleus of a helium atom. In fact, this is where all the helium on Earth comes from. As nuclear decay in the core of the planet occurs, it makes a bunch of alpha particles. They bounce into other things in the planet, steal electrons, and then slowly drift out of the planet, get to the surface, and then get trapped in pockets of the crust. And so when we mine helium, we actually do it at oil wells. That's where we harvest almost all of it. Curiously enough, the oil tends to be where the cracks from under the crust come up. There's actually thought that oil may be produced by the planet instead of a fossil fuel, but we're not certain on that one yet. Nonetheless, this is where an alpha particle comes from. It is ejected from a large unstable nuclei, leaving a slightly smaller and usually still unstable nuclei, a thorium, as well as the alpha particle. So this breaking a nucleus is called fission. This is the vast majority of radioactive decays that we ever talk about. Heavy radioactive materials are things late on the periodic table. They go through fission and break into smaller things. So that's alpha particles. Well, alpha particles are fairly large. So alphas are large, heavy, and compared to beta and gamma, slow. They're still moving a good chunk of the speed of light, but they're slow enough that they can be stopped more easily than beta and gamma. The net result is that these do some damage, but they don't go very far. If you are exposed to alpha radiation, a good layer of clothing is often enough to prevent it hitting you. It doesn't take very much matter for the alpha particle to come to a stop. And so even in the worst cases, not the worst cases, but even in most cases, your skin is enough to stop alpha radiation. It does not penetrate, as I always say. It doesn't dig very deep into whatever it's hitting. So as a result, these have rather low risk. They're lower risk. Lower damage. They will still damage things. Alpha radiation to your hand, it's like the worst sunburn ever. And if you get enough of it, it can do some permanent damage all the way through. Anything enough can. But it is mostly just superficial. As long as your source isn't too intense, it's mostly getting stuck in your epidermis, and our body just sheds that constantly. Scrolling down a little bit, let's talk about beta particles. Beta particles are high energy electrons. So one example, if you have carbon 14, so protons 6, neutrons 8, it breaks into nitrogen 14 and a high energy electron, so a beta particle. Well, the nitrogen has 7 protons and 7 neutrons. So if we look, we've gained a proton and we've lost a neutron. What's really happening is a neutron is becoming a proton and an electron. So one of the neutrons in the nuclei, that's the only place they are, becomes a proton. But you can't just create positive charge. You were neutral. You still need to be neutral afterwards. The universe doesn't let you create or destroy charges. But you can, if you make both, you're still neutral. And so that is what actually happens. The neutron decays into a proton and an electron. Well, the nuclei doesn't have electrons, and so this new electron goes blasting out of the nucleus. This is not one of the electrons that was orbiting the nucleus. This is not one of the normal ones. And that's why this can leave at such enormous energies. It was originally trapped in a very tiny space, and it got launched out with all that energy. And so these are moving at a good fraction of the speed of light. These are small, fast, and they travel deep. Beta radiation is middle danger, or middle risk. So this electron, as you have a bunch of random molecules making up your cell walls or other things or proteins, you can have this electron zipping through and it could hit a couple things, and so you could cause some damage at multiple locations. Beta is able to hit multiple things, knocking other electrons out of the way, causing molecules and bonds to break, and it can go fairly far. Because it's so small, it tends to fit through things, and so it's not going to hit every, you notice I didn't have it actually explode on every part. It'll pass through a lot of molecules and then only hit certain ones. So the idea is it can do more damage because it can hit more things, but it also gets deeper. So your skin is no longer a sufficient barrier. It can get into your abdomen. It can hit your critical organs. And this is why it's more dangerous. If you damage some epidermal or epidermis cells, all right, we just get a burn, get a blister, you replace it. But if you damage part of your kidney, that's a much bigger problem. And so beta radiation is more dangerous because it can dig inside and hurt your internal systems, your critical systems, where alpha was more just on the surface most of the time. You'd have to have a lot of alpha before it did any damage to your insides, really. And so beta radiation is a little bit more dangerous. Well, this leads us then to gamma. So gamma radiation, this can be things like cobalt 60 going to cobalt 60 and gamma. So there are multiple stable versions of some nuclei. And so they can twist, relax, give off energy, but not actually kick out any particles. And so sometimes they just give off a bunch of photons of incredibly high energy. A gamma is high energy photon. Now this actually tends to happen with the others. Uranium going through a alpha decay still gives off some gamma radiation. A lot of beta decays also give off gamma Gamma kind of just comes with the others in various amounts. And so sometimes some materials do an alpha decay give off just a little gamma, and it's not that much of a worry. Sometimes they're accompanied by a lot of gamma radiation, and that's a big reward. So the idea of gamma, just a high energy photon, which means it has no mass, doesn't really have a size, and so it not only can pass right into it through, it can also pass right through you. Digs very deep. So gamma radiation isn't stopped by your body. It will go through your front, pass through your organs, go out your back, and it will have done some damage along the way at every point. And so they tend to hit more things, doing more damage, and they can do it through everything. And so gamma radiation is the higher danger. So these are the three main types of nuclear decay. And we'll give you a fourth here in a second. It's another version of beta. But you've got your alpha, your beta, and your gamma. What is each type of nuclear radiation? And the relative risks of them. Alpha, just, it's bigger, it's slower, it doesn't go as deep. Beta, it's smaller, it's lighter, it's faster, and so it tends to dig deeper and can do more damage to more critical things. And gamma, no mass, just a photon, so it passes right through most things, damaging them along the way. Alright, in terms of sources of radiation, I'm going to stop there. We will introduce the second type of beta in the next video, where we talk about uses of radiation. Why are these things that can cause damage useful to us? Because that's exactly what we want them to do.